balance the following redox reaction. Since we did acid the other day, we're going to do in basic solution. Now, to balance a redox reaction in basic solution, what you really want to do is just balance it in acid first and then do something at the end. So this will be good practice on what we went over Monday, and it should be a little more interesting one. So I'm going to come up here and say manganese per magnate go to mag 2 plus. Balance elements other than hydrogen and oxygen. We don't have any. How do I balance this oxygen? I have to add 4 waters there. Now, what element do I need to balance? Very good. Now I balance charge by adding electrons, and this will tell us whether permanganate is a reducing or an oxidizing agent. What do you think it is? Sorry, it's an oxidizing agent. That means electrons are probably going to be over here. Notice I have +2. What do I have over here? So how many electrons do I have? I think 5 is right. Let's check that out. 5 electrons there. So this is like -6 summed with a +8 gives me what? +2. So yeah, 5 electrons is great. That's what we want. So that half reaction is balanced. Oh yippee, we get to balance an element other than hydrogen and oxygen. What element would that be? Alright, so I gotta go like this. Oh, what about the water business? Alright, so now what do we balance? Charges. I got 0 charge here and -2 over here. I got to fix that up. Absolutely. 2 electrons. All right, now the hard work begins because what's our next step? And can we add both of them together right now? No, we have to multiply to get our electrons the same on both sides. How do we do that? Find the least common multiple in 5, which is what? 10 times 1 by 2 and the other by 5, right? All right, here's where everything can go awry real easily. So I want to multiply this one by 2 and this one by 5. All right, so I'm gonna just write these in. 5 and 10. I'm gonna come up here. 16 and yeah, 2 per magnet. So now we got 10 electrons on each side. We're gonna cancel. 16 proton, 2, 5 oxygen. And sometimes we can simplify, like if I had waters on both sides, that didn't seem to occur. Let's just check all of our elements. I have 16 hydrogens over here, 16 hydrogens over there, 2 manganese, oxygen. 4 times 5 is 20, 28, right? 28, 10 times 20, 28 oxygens on each side. Normally I write these down right here and check that, right? How many, did I do everything? 10 carbons, 10 carbons. What about the charge? I got a +2 here. Oh, 5 times 2 is -10, -12. -12 and +16 is a +4, and I misspoke just a few seconds. Right. So I got +4 on this side. 2 times +2. Over here I got 5 times 2 is 10. 10, 2, +10. What does that sum up to? +4, right? So we want to make sure it's balanced in acid. So we can say thing is balanced in acidic. So to do this, first we have to balance an acidic solution, and then we add hydroxide to neutralize all the protons. So here's what we do. We treat it just like algebra class. I come over here and I say I gotta add 16 hydroxides. Well, the algebra class says what do I gotta do over to this? I gotta add 16 hydroxides. So what does that make? 16 water. So now, just like algebra class, combine these like terms, right? Right. Let's subtract 8 waters here. So I gotta subtract here and go away there with 8. All right, now let's see if this thing is balanced. Man, I got 2 on one side, 2 on the. How about oxygen? Oh, I got 8. 2 times 4 is 16. What's 16 and 8? 16 and 8. All right, proton or hydrogen. Excuse me. Hydrogen atoms. Looks like I got 16 over here, 16 there. Ooh, let's do carbon. 5, 10. I got a 10 in Redox. What's left? Manganese. I got 2, and I got manganese, oxygen, hydrogen, carbon. What's left? The charge. All right, and so I'm looking over here. I got a +4 there. What do I got there? Negative. How about that? -12. 9. Is that gonna work? Oh, look. 5 times 2 is 10. 10 and a -2. I got 12. 12. So to balance a redox reaction in basic solution, 99.99% of the people balance it first in acidic solution and then add hydroxide to neutralize all the protons, and then the rest is just cleaning things up with some accounting. Any questions?
Dude.
Right. It bubbles away perhaps. When I was in graduate school, we had graduate student training to be TAs, and the guy who taught general chemistry for 30 some years, he's all excited, and he showed us how to balance it in base from scratch without doing the acid part first. And I've tried to figure it out by myself, and I can't, and I wish I would know. Attention. No, that was cool. He was excited about it. I have not been able to figure out how to do it just with base from the start. But it follows some type of algorithm like we do with the normal redox. What do we normally do? Balance elements other than hydrogen and oxygen. Balance oxygen by adding water. Balance hydrogen by adding proton. Fix charge by adding electrons. 5 steps. These 5 steps. Don't have one for starting out in base. Voltaic cells. Can electrons swim? True or false? You're close. All right. Look at this picture. So current can pass through water, but what constitutes current in water is the movement of ions. So it's just a humorous thing to get you to realize that electrons don't move through the solution. So here we have what we call a voltaic cell. Could be a battery. And we have some other interesting words, anode and cathode. Looks like the anode is going to get oxidized. Electrons leave. In fact, let's go back to our problem here. What is the reducing agent? What is the oxidizing? Reducing agents supply electrons. Oxidizing agents suck up electrons. So here, for fun, what is the oxidation state on manganese? Oxidation state of I'm going to do this. I got 4 oxygen, -2. This whole thing sums up to 1. Whatever it is on manganese, it's got to make this statement true. You think activate +7. So oxidizing agents get reduced. Let's not worry about that. Let's just relate it back to our voltaic cell. If electrons flow out of this, it gets oxidized. And if electrons come over here, reduction has to be going on here, oxidation occurring here. And we'll see that here. Let's put a real metal. I think you even build this thing in lab today. That's why I wanted to get to this part of the lecture. So here's zinc, 0 valent, 2 electrons are going to fly out. It's going to give me a zinc plus going into solution. Electrons come here. Electrons come onto this copper metal. Notice they drew this solution blue, like we have some copper nitrate. This copper 2+ can see 2 electrons coming its way, jump onto the metal, and go from copper 2+ to copper metal. So zinc is getting oxidized, copper is getting reduced. Zinc is the anode, copper is the cathode. They say not to put a lot of words on a PowerPoint slide. I believe them, but I like to break the rules, I guess. Well, I just kind of told you about all of this stuff. Let's just look at these rules. And I warmed you up with my joke. Rules of Voltaic cells. At the anode, electrons are products. Oxidation is occurring. At the cathode, electrons are reagents. Reduction, and my favorite one you're not going to forget. Electrons die, they drown if they get in the water. No, I don't know. They cannot swim. And then so we got electrons flowing externally. Now, if we put a voltmeter on these things, how many of you have ever played with a multimeter? Voltmeter? All right. Maybe you have like a tail light out on a trailer and you're trying to fix it. That's one reason why you might something like that. Certainly. A synonym for a voltaic cell is also called a galvanic cell. There is a guy who has a name similar to galvanic. I ought to know it, but he was a biologist. He had a thing called a caliper, and he had one piece was brass and the other piece was some other metal, and he was trying to measure frog leg. He's like a biologist, or maybe he was going to cook them up. Who knows? Anyway, he put that calipers that had 2 different metals across the frog leg twitch. And how many of you have a filling in your mouth? Do you like to chew on tinfoil? No, it makes current, makes a battery in your mouth. So yeah, two dissimilar metals coming close to each other, being in solution, you can get some electrochemistry happen. So, and that's how Mr. Galvani discovered electric current. Him and Benjamin Franklin and a few others. People didn't know everything else. All right, oxidation occurs at the anode. We see electrons are a product. Reduction occurs at the cathode. We see electrons as a reactant. Well, this discussion wouldn't be complete without some thermodynamics, my favorite subject. So cell EMF, that stands for electromotive force. 1 volt is a joule per Coulomb. And we use E for electromotive force, so an E cell is a cell voltage. And if we put this little knot symbol, we call that a standard cell potential. A voltage is a potential, kind of like a pressure. Cell voltages with solutions all at 1 molar, gases all at 1 atmosphere, and solids would have a fixed concentration. And what's this E red business? Red means reduction potential. So if we make a battery out of some metals, and if we knew a standard reduction potential for the metal that's the cathode, and a standard reduction potential for the metal that's going to be the cathode, we could measure this. And it says, no, E cell must be positive for all spontaneous reactions. Let me ask you a question. Do you want your cell phone battery to be at equilibrium? Not at all. It's dead when it's at equilibrium. I think I have a bumper sticker on my off-basket door, and it says, old chemists don't die, they just reach equilibrium. So cell electromotive force and standard reduction half cell potential. What's going on with that? So chemists have tabulated electrochemical data. It's like thermochemical data. Standard reduction potentials are measured relative to this thing called the standard hydrogen electron, called SHE, standard hydrogen electron. Here's a horrible picture, it's not big enough. Here's what it looks like. So here we typically have a metal like platinum, and we have protons in solution at 1 molar. We have hydrogen gas at 1 atmosphere, and here's a salt bridge, connects these 2 compartments electrically. So the word circuit means a circle. Well, this looks like a upside down U, but a circuit doesn't have to be a circle. It just means a loop, and it can be bent to any shape. A loop meaning that it's connected. And so depending on what metal's here, the hydrogen electrode could be a cathode or an anode. Here we see it being the cathode. As a reduction occurs at the cathode, here zinc is an anode, and that just has to do with the chemical nature of zinc and hydrogen. So here's the most beautiful thing in the world if you're an electrochemist. This tells you that if you made a single cell battery, the highest voltage you could get is close to 6. And that would have lithium metal as the anode, and it would have fluorine gas as the cathode. I want to build a fluorine gas cathode. It would be impossible to build. But if we look through here, nature was nice, or nature and chemists, they said, let's measure everything relative to hydrogen. We like to say hydrogen's about in the middle. And this is assigned a voltage of 0, and all these others are measured in relation to the hydrogen electron. And so chemists and chemistry students can look at these tables and know what types of reactions are going to be spontaneous and how much potential energy is there. And they can also say what's a stronger oxidizing agent and what's a stronger reducing agent. I'm going to come up here and tell you that fluorine gas is about the strongest oxidizing agent you can have. That's why nobody wants to build an electrode out of this gas. It's hard to work with. It's very reactive. Strongest oxidizing, and this is a strongest reducing. So this table here says a lot. Notice these are all drawn as reductions. A species that has a very positive reduction, and if we're over here in the oxidized form, we have a strong oxidizing agent. It's going to be easy. Now over here on the left, all these things are in the reduced form. So this is in the reduced form, and this has a very negative standard reduction potential. It's going to be easy to oxidize, and that makes it a strong reducing. Now with that, I'll read these bulleted points. The more positive the standard reduction potential, the stronger the oxidizing agent. We've got to realize we're talking the species on the left. It's in the oxidized form. The more negative the standard reduction potential, that means the stronger the reducing agent when we're looking at the species on the right. I could call fluorine anion a reducing agent, but it can't reduce any because of where it's positioned. Like I can call lithium cation an oxidizing agent, but it can't oxidize anything. A species higher to the left of the table of standard reduction potentials will spontaneously oxidize a species that is lower to the right. That means fluorine gas will oxidize about everything. Just enough time to go here. What type of reactions do these look like? Because nobody shouted it out all at once. Looks like single replacement. Luckily, I can look some of these up fast. I'm gonna look these up. Where's silver? There it is. Let me find copper. So this reaction occurs. It's a nice demo when I stick a piece of copper wire and silver nitrate. It's all these moldy and sparked silver hairs growing all over it. You put a piece of silver in a copper 2 nitrate solution, no reaction. So this one is not spontaneous. This one is spontaneous. So here's an equation we saw earlier. How can I put these numbers in here to get a positive voltage? Let me just screw it up. That's going to give me a cell that's less than 0. It's going to give me a number. So what that tells me, I need to put the silver here, the copper there, so I get a positive voltage. And I put the most negative reduction potential. You're saying, Eric, they're both positive. Well, this one's closer to the negative side on the number. All right. Sorry I went over. It's really exciting. In graduate school, I worked for an electrochemist. Good stuff. See you in lab at 1 o'clock.